The dot product is useful for a lot of things. So one of the things that was useful that we found out, and you hopefully found out when you were doing quiz 1, is you can use it to help you find the angle between two vectors, whether in 2 dimensions or 3 dimensions. You can also use the dot product formula that I did. If somebody gives you magnitude of the couple vectors and the angle between them, you can use that formula kind of in reverse and get the dot product, which is kind of cool. So that's just an alternate way to get the dot product. Okay, so let's talk about another use of the dot product, this thing called projections. And this is important. We're going to be doing projections for the entire semester. I'm going to try to introduce it as gently as I can and show you some physics applications of it. So let me draw pictures first, because a picture is worth 1,000 words. So let's say you have U and V, and there, let's say U is pointed here, and let's say V is like here. As you can tell from my picture, it looks like V is lying on the ground, if you will. So here's the deal. We're going to project U onto the vector V, and that's going to give us a brand new vector. What? Yeah, you heard me. We're going to project U onto V. So what does that mean? Well, I'm going to show you the picture first, and then we'll talk about, after looking at some pictures, the actual formula to do it. What I like to do to help students imagine what the projected vector looks like, imagine there's a really bright sun shining up here. The shadow that you would make on V, where V is on the ground, so the shadow that U makes on the ground is a vector. And that vector, I'm going to draw it in red here, this red vector is the projection of U onto the vector V. That's it, okay? And I'm going to call that projected vector, just for now, W1, because I can. Now, oftentimes after you're asked to get a projected vector, like get the W1, a lot of times they'll say, oh, get the vector component of U that's orthogonal to V. What the heck is that? So they'll ask you to get another vector that I'm going to call here, I'll put it in red, it's W2, so that if you add W1 plus W2, it would give you back V. And by using the parallelogram law, I hope you can see that W1 and W2 look like they're making adjacent sides of a parallelogram. Well, here it's a rectangle. And that the diagonal, oops, this is U, sorry. It gives you back the U. So why do we do this? Because our physics brethren oftentimes need to do this, where they like to resolve a vector into its 2 orthogonal components. The W1, which is a projected vector, and this orthogonal component, such that when you add them together, you get back the original. And you may be thinking, why do they need to do that? And we're going to see an actual example very shortly. So let's fill in some blanks first. W1 is called, and I wrote it already, but I'll write it here, the projection of U onto V. Or sometimes it might be referred to, and you want to know all the vocabulary so you could speak intelligently, the vector component of U along V. Same thing, although the more normal phrase is this one. This is more common. Now, I've denoted it W1 so far, but truth is you probably won't see it denoted as W1 in your MyMathLab homework or Briggs, okay? You're going to see it look like this, proj U, and then in a tiny subscript, V. This is the projection of U onto V, proj U onto V. Now, this other vector, W2, which I mentioned that if you sum up W1 and W2, you better get back your original vector U. You can solve this for W2 by simply subtracting the vector W1 from both sides, and you'll get this formula. So know this. And this is called the vector component of U orthogonal to V. Now, this angle right now that we have in my little diagram, I'm not going to find the angle, I just want to mention. This angle here, theta, is an acute angle. Not cute, but acute. So I want to draw you another diagram. What if the angle between U and V is not acute? Let's say it's obtuse, so it's greater than 90 degrees. So here's V again. V will be on the ground again, so here's the ground. And let's say U is pointing way over there. So here your theta is obtuse. What would the projection of U onto V look like now? And this is key that you get this. Once again, the first grader definition is, let's look at the shadow that U would make on the ground if there was a bright sun shining high above. So the shadow that you would make on the ground would be this red vector I'm going to draw right here. Oops. And notice it's pointing in the opposite direction of V. So this is my W1 picture here. And W1 is the same as the projection of U onto V. But it is pointing here in the opposite direction of V. Either way, the projection is parallel to V. So whether it's pointing in the same direction or the opposite. And then you can still get W2 the same way. And in my picture here, W2 would still be this orthogonal component. In other words, it's making a 90-degree angle with the W1, such that the sum of W1 and W2 had still better give you back that original vector U. Okay? So there's your pictures. And now I haven't told you how to get the projection, and now I'm gonna. And you're probably not gonna like it because it's kind of looks complicated. Okay, so here's the big formula, people. Drum roll. The projection of U onto V is, now before I give you the whole thing, I do want to say, because of looking at, you look at my two pictures here, this projected vector here is parallel to V, whether it's pointing in the same direction or the opposite. And one of the things I hope you got from last week's material is that when two vectors are parallel to each other, one is a scalar multiple of the other. So this projected vector is simply a scalar multiple of the vector V that's on the ground. So this right here is a scalar, and we're multiplying it times V. So the scalar, the pure number, is found by the following. The numerator, you take the dot product of U and V, and in the denominator, you divide by the magnitude of V squared. Now here's the weird part about this formula. You know how we're projecting U onto the vector V? In this formula, which vector shows up more times than the other? The U or the V? I'll open it up.
V.
Good. Isn't that kind of weird, even though we're projecting U onto V? Yeah, and that's key that you know this, because on your homeworks, if you do this backwards, you accidentally say, oh, the U is supposed to show up more than the V when you're projecting U onto V. And you do it all back-asswards, I'm not going to give you any partial credit. Zippity-doo-dah. Know this. Now, there's an alternate way that Briggs, Briggs, did I mention that Briggs sucks yet? Not today. There's a couple alternate formulas that I'll be okay with, although I prefer if you use this one. But let's use one that should be obvious, like, Captain Obvious. So you'll still have a scalar times V. Do you guys remember that we did a little cute little theorem, and the property basically said that the magnitude of a vector squared is the same as the dot product of itself with itself? Do you guys remember that?
Yeah.
Okay,
Yeah.
good. So these are equivalent, and so you can pick your poison. Some people prefer this version because oftentimes when they're doing the magnitude, they forget to square it, and then they get it wrong, and then they get all upset. So that's fine. But now I'm going to show you a Briggs version, which I think kind of sucks, but it's still legit. But when you hit the View an Example button, unfortunately, Briggs is going to probably show you this version, which makes me unhappy, but I don't have any control over that, what they show you in the Briggs version. but it's kind of good review. So hopefully you recall that the dot product of two vectors can also be found in an alternate way if they give you enough information. And so what I mean is u dot v is cosine of the angle between them times the product of their magnitude. So that's equivalent. And then everything else is going to stay the same. So we still have v here. I'm going to use the denominator that I started with, which was the magnitude of v squared. And now do a little bit of reducing to lowest terms. So you'll notice that this magnitude of v cancels one of the magnitude of v's downstairs. And so your MyMathLab will say, well, the another alternate version of projection is going to be this scalar times the vector v. And that's okay also, but you have to have the angle between them. And a lot of times you don't. So you can only use this formula in certain cases. Okay? So now there's another thing that I'm going to ask you on quizzes and do on homework. What is the scalar component of u in the direction of v? And you might, some of you might, because it seems, oh, you just said that here's the scalar right here, right? There's the scalar. It's going to be that. No, it's not. So you have to be careful because it's the scalar that would multiply by the unitized version of v. What the heck? So I'm going to derive this formula before. I'm not just going to hand it to you right now. So what do I mean? Let's take my version of the projected vector of u onto v and rewrite it a little bit. I'm going to take one of these factors of the magnitude of v and put it under the denominator, and the other factor of the magnitude of v squared there will go here. And this is the unitized version of v. And so this right here is the scalar component. That's how you get it. That's how you get it. Really? Yeah, really. Now, the Briggs has another version of, so here's another way to get the scalar version. So if you look at Briggs, this is Briggs' projection formula. If I move the magnitude of v underneath the v, so I move, so this is just going to be a 1 here, and then I have v over magnitude of v. This is the unitized version of v. Okay, great. And then the scalar that's multiplying with that is the scalar component. So there's two versions, and they both better give you the same number, okay? They both better give you the same scalar. So you can either use u dot v over magnitude of v, or if you were given the angle between the two vectors, the scalar component will simply be the cosine of the angle between them times the magnitude of u. Now, another reason why I can tell you I hate Briggs is Briggs' version of that cosine angle thing. If you don't have the cosine of that angle, then you have to go, well, how do I get it? And then you have to use that formula that we learned last Friday. Big pain in the butt. Okay? All right, let's do an example or two. So, how do you decompose a vector into its components? So here's an example, basic example. You're going to see it in the homework. And good news, you'll see it on the quiz. Okay, so they're giving you u, and they're giving you v, and they're giving you u and v in what kind of format? I'll give you two choices. The component form or the linear combo of the standard unit vectors. Which one of these two formats are they giving us?
Linear combination.
Good, Aloe, thank you. Exactly right. Once you have those IJKs, that's the type of formula that we're given. Okay, fine. So now what? Well, they want us to find the projected vector of u onto v. What does this mean? It means get proj of u onto v. That's all, which is a vector. So you're going to go proj of u onto v, and you're going to look at your formula. How the heck do I get that? Oh, look at all these choices. I could use that formula or that formula, and they didn't give me the cosine of the angle between them. So I claim that the Briggs formula, you could do it, but it's a big waste of your time. Quicker to use my way. So I'm going to use my way, which is, oh, it's a scalar times v, and the scalar has a numerator of u dot v, and the denominator is the magnitude of v squared. Okay, so let's just do this. The dot product is 3 times 7 plus negative 5 times 1 plus 2 times negative 2. How did I get all that? Well, I'm just multiplying the x components, the y and then add that to the product of the y's plus product of the z components. And then this is a magnitude squared, and it's v's magnitude. Be careful, not u's. You blow this, I got no mercy for you. Sorry. And then that's a scalar times the vector v. So it turns out that the numerator is 12. And then the denominator is, okay, 49 plus 1 plus 4. Oh my goodness, what the heck? I get 54, so it's square root of 54 squared times the vector v. So 1254 does reduce, so please reduce it. Otherwise, I dock you a point every time you don't. Both 12 and 54, I think, are divisible by 6. So let's do that. So this is 2/9 times the vector v. And so it's really 2/9 times, and I like component form myself. And then using your knowledge of scalar multiplication with a vector, distribute the 2/9. So 2/9 times 7, comma, 2/9 times 1, comma, 2/9 times negative 2. So I'm going to give my answer in component form. Okay, any questions on letter A? I just got the projected vector. Yay, success.
I know you answered this question like last week, and I forgot the answer. I'm sorry, but is it okay if you represent a magnitude form of vectors as a single bracket as opposed to two of them, because it looks really ugly and my hand cramps up whenever I do it?
I prefer that you do it the way I've been teaching you with the double bars, but I get that Briggs uses single bars.
All right.
I'm not a fan of single bars. Why? Because it kind of looks like absolute value notation.
Okay.
I'm just saying. I'm not going to like dock you or anything like that, David, if you decide to use the Briggs version. But did I mention that Briggs sucks yet?
I think the second time this week only.
I know, right? Okay. Does that answer your question?
In spades.
Okay, cool. Now, part B, find the vector component of u that's orthogonal to v. What the heck are they asking me to do? Oh my goodness. They are asking in my picture.
Did she freeze for everyone else?
Yeah, it's totally totally frozen.
Okay, cool.
So how was that quiz?
Good.
All right, fair enough. I don't know what to say. Yeah, it was pretty good. Yeah.
I thought we were gonna take it at class time.
Yeah, no. I examined the email closer, and then my fucking we're recording. I keep forgetting that.
David, you should have known though. We had her last semester.
I have the memory of a goldfish, and I'm pretty sure that if I don't write down for me to breathe, I will literally die of suffocation because my brain cells have been completely obliterated with my years of lack of sleep. So I'm pretty sure that it is a miracle that I looked at the schedule at yesterday at 12 o'clock and realized that it was actually due by the time class started. So that was a fun 2 hours, or 1 hour and 1 minute and 75 minutes.
I wish I had your foresight.
There was no foresight whatsoever. It was complete coincidence that I managed to do it. There's a very close parallel universe to this one where David just slept through the quiz and then saw that it was due today and then proceeded to I don't know, be very upset at himself.
I like the facial hair, dude.
Thank you. It took me a lot of minoxidil to grow it.
Is she gone completely?
Yeah, 100%. Someone else is the host now. We need them to teach them. Yeah, hey Rick, teach us some vector calculus.
Oh, she realized she dropped. She might still be going on without us.
Yeah, sometimes she'll for a little bit and then she'll come back and say sorry and
Wait. She's back. She's back. She's the host now.
Professor, you're muted.
Can you hear me now?
Yes.
Yes.
Okay.
You're golden.
I have really, really bad internet, so I apologize in advance of crapping out all the time. I spend over $100 extra per month on having better internet. I bought a new router recently, and it's almost like it's worse now.
Do you have an Ethernet connection to your router or no?
I've tried everything.
Oh, I see.
I'm so frustrated beyond belief. I can't. I don't know what to say other than
I just wanted to mention I used to have Cox, and in my area they were just the worst. They were giving me,
Cox
like,
is a scam. Like, seriously, like they don't sell Wi-Fi. They sell like microwave like radiation in a box that might work sometimes, you know?
I made the switch to AT&T, and I'm so much better.
You
I'm
guys
stuck
are
with
so
Cox.
funny.
It's over.
Okay, W2 is a vector that's perpendicular to W1. W1 is just the projected vector we just got. It's a perpendicular vector. Orthogonal member pretty much means perpendicular. And it's real easy to get. The projected vector is kind of hard, as you saw. You got to do all this formula. It's just going to be your original vector U that you were projecting onto V anyways, minus your projected vector, okay? So you already know what U is because they gave it to you. I'm going to use component form if you don't mind. Minus this projected vector that I just got. I know we have weird numbers, but we've got minus 14/9, 2/9, and the negative 4/9. And then, of course, you're going to, don't ever give me decimals. I'll dock you points bad. So this is going to be the vector 3 minus 14/9, negative 5 minus 2/9, 2 minus a minus 4/9. Put it all together, do the arithmetic, and you get these weird fractions. 13/9. I think that's negative 47/9, but I can't read my own handwriting. I watch old episodes of Law and Order, and I love Lenny Briscoe. There's the Lenny Briscoe drinking game, but the drinking game is you take a shot anytime he makes a sarcastic remark. So the other day, his sarcastic remark was to his partner, "Hey, can you take notes? Because I can't read my own handwriting." Okay. Sorry, I just think that's funny. Here's your final answer, okay? Now, who cares about any of this, and where do you use this projection and get the orthogonal complement in real life? Physics. So I'm going to draw a physics picture, and some of you are going to poop your pants, you know? So I'm just warning you in advance. But I want to I'll draw the whole picture with the force diagram and the whole shebangy, and then you have to get that you need to care, because, yeah, it's going to be on quizzes and exams.
Oh my god, I actually remember seeing this stuff.
It might actually make sense now, David. Good news. You probably didn't even know what the heck you were doing then.
And I
All
still
right,
probably
so
won't.
you've got a 30-degree angled ramp. So I'll just try to draw a ramp that's somewhat of a 30-degree angle here. And you've got a trailer and a boat sitting on the ramp, okay? You know, I'm not very good at drawing boats or trailers. So if you could just sort of bear with me here. This is pretty disgusting. You know, all right, there's a boat sitting on a trailer. I hope you could get behind that. So we're going to be asked to find two different forces, okay? But before I figure out what those unknown forces they want me to get, let me just tell you about the force that's already there. It's the force due to gravity, okay? You can't have scorn for the laws of physics. So this boat and trailer weigh 600 pounds. So there is a downward force down into the center of the earth that I'll call it F, that has a magnitude of 600 pounds. And if you want to, you can overlay your rectangular coordinate system on top of this picture. Here's the y-axis, you know, I don't know, if you want, you know, like here's the x-axis. And I hope you can see that if 600 is the length, this point here has coordinates 0, negative 600, which means the component form of that force is 0, negative 600. So we have that force. So what are the other two forces they want us to get? They want us to find the force required to keep the boat from rolling down the ramp. So I don't want to get macabre or anything too much here, but if you were standing here and let's say you were trying to push against the boat and the trailer to prevent yourself from getting ran over, what force would you have to push up against the boat and the trailer so that it doesn't run you over? So
What's
that's,
the coefficient of kinetic friction, though?
we're not going to have friction, okay? We're going to,
There's no friction.
yeah, no friction, sorry.
All right.
Let's just go with, you know, frictionless idea here, just to keep it easy, okay, David? I don't want to confuse too many people. Not everybody in the room is seeing physics.
I got it. I got it.
That's one of the forces they want us to figure out. The second force is what force must the tires of the trailer withstand? So that force is these tires are kind of, you can think of them pushing into a perpendicular to the ramp. They're pushing down that way. And that's the force that the tires have to withstand. Okay? So I've kind of gotten a little messy here. So I'll try to, but here's the plan. We're going to project this force vector, big F, onto the ramp. We're going to project this force onto the ramp. So you have to think upside down. Remember I told you that a sun is shining and its projection is the shadow that the vector makes on the vector that you're trying to project onto. So if this is our ground now and there's a shiny sun that's shining up, the force vector, this force vector projected onto the ramp, there's a, you know, sort of shining this way, is going to be, and I'm just trying to draw this the best I can, it's kind of hard to draw upside down, is going to be this red vector. Let me get rid of that little man. It's going to be this red vector here. So this is the sort of the shadow it's making. So this is our W1 vector. So that's what we're going to find here. So W1 is the projection of the force onto a ramp vector. And we need to find this because nobody gave us a ramp vector. And I'm going to show you a quick and dirty way to get one in a second. But then this is basically asking us to find W2. So W2 is by default perpendicular to W1, and that's going to be the force that the tires have to withstand. Okay. Now, what the heck is a ramp vector? They didn't give us a vector on the ramp for us to project onto. So here's my claim. The ramp vector, I'm going to say, because I'm the boss here, I'm going to create one. I'm going to form one. I'm going to make it a unit vector that lives on the ramp that's making an angle of 30 degrees with the horizontal. So I'll pick a different color to draw the little ramp vector, okay? So I'm going to just draw it from here in the corner. Just say, this isn't really the origin, but it could be. He's just this little pink vector here that's making an angle of 30 degrees with the horizontal. So I'll call him U. And because I decided he's going to be a unit vector, by default, what is the magnitude of a unit vector?
1.
Thank you, whoever said 1. I appreciate that. So it's going to be pretty easy to give, so this is a 1, these magnitudes I have here for the unit vector. So the unit vector has components that are simply cos 30 degrees and sine 30 degrees. So square root of 3 halves, I think 1/2. So, and you can move this vector anywhere you want, because remember that cool fact that a vector represents infinity vectors as long as all the other infinity vectors share the same direction and the same length. So if I move this vector over here, you know, that's fine, and I'm going to project my force vector onto the ramp vector. So that's how I'm going to roll. So and that's how our physics brethren roll. So this projection onto the ramp vector is going to be equal to the force vector dotted with my little unit vector all over the magnitude of the unit vector squared times the unit vector. That's the formula for projecting. Now, good news, this denominator is super easy because, once again, what is the magnitude of a unit vector?
1.
1.
1. So 1 squared is
1.
1. Right. So this projected vector is going to be the force vector dotted with the unit vector. Okay, let's do that. So we have 0 times square root of 3 halves, that's 0, plus negative 600 times 1/2 all over 1. times the unit vector. And so this dot product ends up being what? Negative 300. Now you could distribute the negative 300 over the unit vector. I'm going to hold off on doing that just for the moment. I am going to need to do it for part B. But what's the magnitude? So what's the magnitude of this projected vector? It's basically the magnitude of this vector I just got here, which is this scalar times the unit vector. Sorry, I'm having to write tiny. Now, the reason why I'm holding off on distributing the negative 300, because I gave you a fact from last week's lecture. And the fact was this: if you take the magnitude of a scalar multiple, it's the same as the absolute value of the scalar multiple, the positive version of it, times the magnitude of your vector. So using this fact, this magnitude of this projected vector is going to be the absolute value of the negative 300 times the magnitude of this unit vector. But what is the magnitude of a unit vector? Quick, come on.
1.
1.
1.
300 times 1, and I'm done with part A. The answer is 300 pounds. The force that you'd have to push standing right where the boat's going to run you over, this red vector here, that magnitude is 300. So you'd have to push back with 300 pounds so you keep your boat from rolling down the ramp. Okay? Answer to part A, 300 pounds. Now, part B, they want the magnitude of W2. So how do you get W2? Well, by default, W1 plus W2 is supposed to be equal to that original force that you were projecting in the first place. So if you just subtract W1 from both sides, and remember W1 is the projected vector, same thing. So it's, I'm just giving it this other name. It's a little bit easier. So you're just going, what is the 0, negative 600? That was our force factor. Minus, now this projected vector, remember, was negative 300 times that little ramp vector that I created. So this minus is going to give us a plus, and then if I distribute the positive 300 over my little unit vector, I'll get, after doing a little bit of reducing, 150 square root of 3, and then negative, or I guess that's going to be positive 150, because we did the positive. And then add these two vectors together to get your W2. 0 plus 150 square root of 3 is 150 square root of 3, and negative 600 plus 150 is negative 450. And so then you'll find the magnitude of W2, and that's going to be the square root of the sum of the squares of the components, and then whip out your calculator. And I'm going to round this to the nearest whole pound just because I get roughly 520, and the answer is 520 pounds. So the tires have to be able to withstand 520 pounds. Okay. Woo! Let's stop there and see if anybody has some, yeah, it's a frictionless trailer and so on.
Professor, can
Yeah,
you
everyone-
scroll up
Yes, George.
to can you scroll up to the boat raptor?
And yes, sorry if you're running out of room in your course reader. I should probably leave more room, but that's why on the each page, the back side has blanks. So feel free to use those blanks to do a continuation.
Oh yeah, I just have a question about the setup.
Sure.
So what if you wanted to have the coordinate axis tilted to the slope or the ramp? So let's say you wanted to have the y perpendicular to the ramp. Would that have the problem easier, or?
Real normal force
I
hours.
personally don't like that way, because then I would have to come up with an alternate component form for my force vector instead of the easy peasy 0, negative 600 where it's on the y-axis itself. It'd be a little off kilter there. So you could if you want, but I think it's going to make your problem maybe 10 times as difficult.
Oh, so it's better to just have in that normal orientation then.
Yeah, Remember, when you're doing a physics problem, if you haven't taken physics yet, I'm just training you. When you're given a force diagram type problem, it's up to you where you want to overlay your coordinate axes. But you always want to try to, play a smart game, be the smart rat, and pick it where it's the least amount of work possible.
Okay,
I don't
thanks.
wanna
As many
think too
forces
much.
on the axes.
Mm-hmm. Yeah. Unless you like pain, in which case knock yourself out. Okay, let's do work.
Oh, Professor, I have a really bad question actually. What is does the arrow above a variable refer to the component of the magnitude, or am I just
No, the arrow means it's a vector,
vector? Okay, so like
as
vec-
opposed to being a scalar.
that's it? Okay,
That's it.
all right.
In fact, I'm about to discuss work, so your question is a perfect segue to my next topic. We're
Yippee.
going to discuss work. And yes, this class is a lot of hard work. And work is a scalar. So when I write W representing work, I'm not going to put that little arrow thingy dingy on top because work is not a vector. So the work W, and notice this is not in boldface because it's not a vector, it is a scalar, is found by, you have to, a force does get involved when you're figuring out work. But the idea is, and let me draw a picture, and if you haven't had work yet, I know in Calc 2 you might have had a little introduction to it. These days I don't usually cover work anymore in my Calc 2 because I just don't have time, and I figure you'll either get it in your Calc 3 or your physics or both. So we're going to cover it here. Let's say you had a big granite.
Professor, are you still recording?
Yes, I am, Rick.
Okay.
It's still going. Did you want to stop?
No.
Okay. Let's just say that you had a big piece of rock on the ground again. We did something like this last time, but it was a completely different type of application. We were just adding vectors. Here, we're not doing that. We're computing the amount of work done on this big piece of rock if we were to pull it in the same direction as the line of motion, so along the ground, like along the ground. So folks, work, when you get work is basically, there has to be some motion involved, otherwise no work is being done. So it's found by the magnitude of the force, and the force has to be in the same direction as the motion. And if it isn't, you want the component that's going in the same direction of motion, multiplied by the distance that an object moves. So here, if we were able to move this rock to say way over here, so that the point P ended up over here at the point Q, work would be the magnitude of the force that we're pulling times the magnitude, since this from here to here is distance, it would be the magnitude of the PQ vector. That would give us the distance, okay? Now, folks, you're never going to use this formula in my class. Why did you even give it? Because that's sort of the baby beginner formula. The reason why you rarely use it is because usually you're not lucky enough to have your force vector be parallel to your line of motion. Usually it's a little off kilter. So let me give you the type of problem that's more common to this class in physics. So same rock, he's on the ground, and this time, let's say your force is a little off, it's not pointing in the direction of the motion. The motion is still going to be along the ground, and the rock will still end up over here at Q. So what you're going to need is the angle that the force vector is making with the horizontal, and then you're going to be able to hopefully use that to help you get the part of the force that is pointing in the same direction as PQ. What is that? It's this red vector here, which is the projection of force onto PQ. This red vector is the only part of the force that's helping or contributing to the rock being able to move. Any other component of the force is not helping the rock move in the direction forward. So this is what we want. And so the work formula here is going to be the magnitude of that projected vector of F onto the PQ times the distance moved. So this is a formula you can use, but I'm actually going to make it easier so that, again, you're probably not going to use this formula. And I'm crossing these out for a reason, because if I see you use them on any quiz or an exam, I'm going to go, what are you doing, since I gave you easier formulas to use? But I'm going to use this to derive the good formula. So what do I mean? This red vector is what we want. But if I drop this perpendicular down, we have a right triangle here. And what we're going to use is our knowledge of cosine theta is equal to adjacent over hypotenuse. So if this is our angle theta, cosine of our angle is equal to the magnitude of that projected vector onto the ground vector divided by the hypotenuse, but the hypotenuse is the length of the original force vector, and then solve this for the numerator, the magnitude of the projected vector of F onto PQ. And when you do that, you get that it's equal to cos theta times the force vector. So you're going to actually substitute that into this first factor, and that is the formula I want you to use. So this is formula number one. Write this down. W is equal to cos theta times the magnitude of F times the distance the object moves, which is the magnitude of PQ. This is an awesome formula for work, and I'm totally okay with you using it, so go for it. Now, sometimes that formula isn't helpful. Well, why not? Because a lot of times they don't give you angle or magnitudes of the vectors involved. Sometimes they'll just give you the complement form of the vectors involved, or you have to, or some points where you may have to form a vector. And you're like, what? And so you may want to use the dot product form. So before I give you the dot product form, let me remind you of a formula you were supposed to have learned in order to do your quiz yesterday and turned in this morning. Do you remember that the dot product of two vectors is the same as cosine of the angle between them multiplied by the product of their magnitudes? Please say yes.
Yes.
Yes. I'm going to use this formula backwards. I'm going to use it backwards. So do you see that the right-hand side of this formula kind of matches the right-hand side of formula one? But instead of u and v, it's what vectors?
F and PQ.
Thank you. So the alternate work formula that I'm okay with you using is, somebody wants to know the work done on an object as it's operated on by some force, and then the distance it moves is the same as, if you're given the 2 points, you can just get the PQ vector. There's the dot product form. They're both good because they're both equivalent. Well, which one should I use when? I'm confused. You'll know, because the word problem will give you certain pieces of info, and it'll be like Captain Obvious on which formula will be the easier one for you to use. Okay, so let's do 2 problems, and the hint is one of these problems will involve one of the formulas that I gave you for work here, and then by process of elimination, the other problem will involve the other version of the work formula. So we'll done both versions. Okay.
First,
Take a
quick
look
question.
at problem number 1.
Quick question.
Yeah.
Is projection just Newton's third law?
Is projection what?
Just Newton's third law?
I don't know which Newton's third law is. I'd have to see it, so I'm not going to answer that. It's
Okay.
a possibility it may
So-
incriminate me, because the only real thing I remember from my physics days is F equals ma.
If that helps, it's the other one you ever use. It's for every action, there's an equal opposite reaction.
Right.
Yeah. Okay. I'm not so sure projections are that. When I think of projections, again, I just think of a contribution
Okay.
of a vector in a certain direction. That's
All right.
all. Like one way that you can think of, when I see, look at this piece of granite formula. Instead of a piece of granite, can you imagine one of those little rides at Disneyland or a roller coaster where this is a box car where you're in it? And then here are the rails of the roller coaster ride or whatever. Ooh, shoot,
Oh,
thing disappeared. Well, I hate PDF annotate. Anyway, what I'm getting at is, let's say somebody had a rope tied to the little box car, even though the box car is on the rails, so it can only move forward along the rails. So if you're pulling at an angle to the box car, it will move along the rails, but only the portion of your force vector that's pointing in the direction of the rail, you know, the train tracks or whatever the little ride is on, is going to contribute to help the little box car move along the little train tracks. Does that make sense?
yeah.
So that's the idea of projection. It's like the part that's contributing in the direction that you are kind of moving.
Right.
Okay?
It was a question more of curiosity, right? Because like I'm finally seeing how physics works and just excited. That's it.
It is exciting. So congratulations if it's all making sense and coming together now. Maybe it's a day late and a dollar short, but better late than never. Okay, so which one of the two formulas, folks, to close a sliding door, a person pulls on a rope at a constant force of 50 pounds at a constant angle of 60 degrees, find the work done in moving the door 12 feet to its closed position. And be
You got
sure-
angularity, so maybe the projection form.
So which form, the projection or the dot product form?
Projection.
Both work. I would.
No.
No?
You are only able to use the projected form. Why?
Okay.
Because they gave you the distance. This is basically the magnitude of PQ business. They gave you the magnitude of the force, that's 50 pounds, and they gave you an angle. There's your theta. So you have all the ingredients to bake this cake. So the work done on the door is going to be cos of 60 degrees times the force, that's a 50-pound force, times the distance, in this case it's 12 feet, and then what the heck is cosine of 60? Crap.
1/2.
Thank you. So this is 1/2 times 50 times 12, and I get 300. But if you just write 300, I'm going to dock you a couple of points because I want the units. So, you know, what are the units? Miles, inches, seconds, what? And if you're
Joules, right?
Physics,
Joules,
you may
anyone?
not know the answer. It's
Am I
called
crazy? Like,
Foot
It's
pounds
called
for what we
foot
have.
pounds. Foot pounds. I'm not making this up. You better, and it's not pounds feet. Like if you do this back ass words, won't give you I won't give it to you because I'm trying to teach you tradition here. Foot pounds. Now letter B, we're going to find some work done. Which one of those formulas do you think we're going to use? Here they're giving us a point P where the object starts and then it ends up at the point Q. And the magnitude and direction of the force vector is this vector here in component form, where the distance now is measured in meters and the force is measured in newtons instead of pounds. Make sure you give appropriate units in your answer, okay? So I hope this is obvious that you are going to use the dot product form, okay? But you're going to take the dot product of V, which is the force, with the, do I use P or Q or neither?
it's gonna be
You have to merge
Q minus
them.
P, right?
Yeah.
No, you have to have a vector. I hope you get the difference between a point and a vector. And I know some newbies still don't have that in their brains yet, but I'm trying to train you.
Don't you have to?
This has to be, you can only take a dot product between two vectors. You can't take a dot product between a vector and a point. That's impossible and it's meaningless. So be careful. What am I doing here?
Find PQ.
Thank you. So step one is I can't even find work yet. I have to form the vector PQ first. And if you neglect that step, I don't care what else you do, the whole problem, you just lost 20 points. Congratulations. You blew it. So the PQ vector, and yes, order matters. You're going to do terminal minus initial. And you're going to take the difference of the x coordinates, comma, take the difference of the y coordinates, and then take the difference of the x coordinates. So here I'm going to get -4, +1, and -4. Okay, now I can go ahead and do the dot product with the force vector and the vector that basically connects the starting point with the ending point, okay? So I'm going to take this force vector to -4, 3 and dot product that guy with the PQ vector, because it's meaningless to take dot product of anything except for two vectors. And then using our knowledge of dot product 2 times -4 plus -4 times 1 plus 3 times -4, and do the arithmetic, and I get negative. Ooh, is it even possible to get a negative work done? Any physics buffs in the room?
Yes, yes, it's true. It's true.
Yes, work can be positive, negative, or 0, as a matter of fact. And for those of you who are like, wow, this stuff is really boring and I'm going to just tune out and fall asleep, you can, but we're going to be doing a hell of a lot of work on the last 3 weeks of this semester. In fact, that's all we're going to be doing practically, is finding work done by vector fields on objects as they move around within the vector field, like some magnetic field or electric field or something like that. So don't lose sight of the fact that work is really important in my class. Now, what are the units? -24 watts. Not foot-pounds this time, because we're in the metric system. So there's 2 answers I'll accept. One of them is Newton meters, or you can write -24 capital letter J, where J stands for, anybody know?
Joules.
Joules, thank you very
Joules.
much. Joules
The
means
real
the same
unit.
as meters. Same. Okay. Now, David, about the running out of course reader room, I try to give as much room as possible, but sometimes if I give too much room everywhere, the course reader starts ending up being lots and lots and lots more pages, and they charge me by the page. Not me, because I don't have to pay, which means actually they charge you by the page. So if you think my course readers was expensive at what, it was like 50 bucks. If I doubled the pages, then you would have had to pay 100 bucks, which would be a drag, okay?
All right.
So I am done with this section, yay, and we're gonna move on and do the cross product of 2 vectors in space. So what the hell is that? Well, you're gonna see what cross product is in like 2 shakes, don't worry. For those of you who are in my Math 130 class, which is awesome, I love that class. That's my programming class. You'll probably note that that class has like a 600-page course reader, which means it's expensive. So just because the nature of code, there's so much code in that book that it's just huge. Okay, we're going to do cross product now. So what the heck is that? We're getting there. So I'm going to teach you what cross product is, and then we'll look at some other applications of cross product, and one of them is torque. There's all sorts of cross product physics applications in particular. For those of you that are taking linear Math 254, may I remind you, you are going to do some fun and play with vectors. So a lot of what we're doing here right now, this first 2 or 3 weeks of the course, good news for you if you're in Math 254, because right around October, you'll probably get into chapter 5, and they're going to deal with vector spaces. Don't ask me what that is, but it's cool. And you'll be dealing with a lot of some of the same concepts that you've already seen here on a somewhat different level, though, just so you know. But you can thank me later. Okay. Oh, I already see a typo. That's okay. So the cross product we're going to define right now. And it's not going to make sense, but just try to go with it. It's denoted with a cross instead of a dot. So it's a different kind of product of 2 vectors, and they say U cross V, so there's a little double quote missing there. It's a vector, and what vector is it? It's a scalar, of course, times another vector. And the scalar is the product of the magnitudes of the 2 vectors you're taking the cross product of multiplied by sine of the angle between them multiplied by n, where n is a unit vector that's perpendicular to the plane containing u and v. What? According to the right-hand rule. So if you're left-handed, please do not get a resentment, okay? It's not against you. So I'm going to teach you the right-hand rule right now. Here's a picture. If you have two vectors in the plane, so u and v are somewhere in this plane right here. Plane kind of means flat surface at this point. If you wrap your fingertips first going through u and then close your fingertips through v and not have your thumb involved, like you don't want to make a fist, just have your thumb kind of sticking out, the direction that your thumb is sticking out is going to be the direction of the cross product, and that's why they call this the right-hand rule. If you did v cross u would be another vector. It would be pointing downward. It would still be orthogonal to the two original vectors, but you would first have to put, because order matters, your fingertips would first have to go through v. You'd have to kind of sort of put your hand opposite, and then your fingers would close down on you, and then your thumb would be pointing down. Now, for those of you who think this crap doesn't matter, like, yeah, whatever, I'm going to give you a quiz or homework problem. Well, I will ask you if you think that the cross product of two vectors is coming out of the paper or going into the paper. And if you answer wrong, you're going to miss a lot of points, because that means you don't get this right-hand rule. And yes, it matters. Like if you go to a physics class, you can't do the right-hand rule, you're dead. One of the things I remember when I was going to UC Berkeley as an undergrad, we were all sitting in this huge room, like 500 people, because all the undergraduate physics 1 classes had to take their final on the same Saturday morning in the same room. And I remember, and they have 3-hour finals. In the middle of the final, I looked over across the room and everybody was doing this. Look at my video, look at my profile now. They were like doing this. They were like, you know, trying to get underneath their hand or their arm, and they were all like scrunched over in weird positions, trying to use the right-hand rule during the final, and I just died laughing. Oh, God, it was funny. Okay, so this formula that you see here, you're never going to use it. So basically, I'm just going to put a little note here, we'll never use. Seriously. Well, how are we going to get the cross product then? I'm going to tell you on the next page. You're going to use the determinant way to get it. So if you know how to take the determinant of a 3x3 matrix, congratulations, this will be sort of easy to get. If you haven't, don't worry, I'm going to walk you through it. So the first thing you're going to do is across the top row of this 3x3 matrix, essentially, you're going to put I hat, J hat, and K hat. For the second row, you're going to put the components of U, because he's first. So just put his components, whatever they are. And along the bottom row, put the scalar components for the V. Now, what this is going to give you, it's going to give you equals a 2x2 determinant multiplied by I hat minus, and it's really key that you get a minus here, a 2x2 determinant times J hat plus a 2x2 determinant times K hat. That's how you get a 3x3 determinant when you expand along the top row. Don't ask me why this one's a minus and why this one is a plus. Then I'm going to have to get into some linear algebra topics, and I don't have the time. So go look there, and it's because of the matrix of cofactors. Go talk about it there. But these 2x2 determinants are easy to get, but you have to figure out what do you put in these blanks that I left here. Watch closely. If I were teaching face-to-face, this would be a lot easier to teach you. Unfortunately, it's hard. But to get what this 2x2 determinant is multiplied by I hat, temporarily block out the row and column that I hat lives in and look at the numbers that are sitting there. Those numbers go into this 2x2 determinant. What about the 2x2 determinant multiplied by J hat? Block out the row and column that J hat lives in and look at the numbers that are still left standing. Copy them down. Similarly, to find the 2 by 2 determinant for the k-hat guy, block out the row and column that k-hat lives in, and look at what's left, u1, u2, v1, v2, okay? Now what? Now you still got work to do, I'm not done. It's easy to find the determinant for a 2 by 2 matrix. You simply multiply the two numbers along the major diagonal, and this is key that you get this, so whatever u2 times v3 is, minus the product of the values that live on the minor diagonal, u3, v2. And that's going to be a pure number. Multiply that pure number by I hat. Minus, and then you're going to do the 2 by 2 times j hat, major diagonal minus the product along the minor diagonal, oops, times k hat, plus the 2 by, oops, that's supposed to be j hat, my bad, plus the 2 by 2 determinant multiplied with k hats. You're going to go u1, v2, that's the product along the major diagonal, minus v1, u2. And there is your formula for finding cross product of two vectors. Let's actually do some examples now. Here we go. You're given two vectors in space. There they are. Cool. Then, David, nobody knows variation of parameters unless they've taken differential equations, okay?
On the offhand, you know, like maybe.
We're just trying to be a show-off here.
No, like listen. Okay.
Yeah.
I will
People
refrain.
out. Like they're going to go, is there something I'm missing in this lecture? Because this lecture has nothing to do with variation of parameters.
I was wondering if there was a fellow like DiffyQ survivor among us, but like no.
The Wronskian is essentially a determinant, okay?
Fair enough. I'm not trying to show off, Elva. Okay.
Okay. So if you're following my lead on how you're going to find the cross product, I'm setting this up where I'm going to do the 3 by 3 determinant method to get my cross product of u and v, okay? So that's going to be a 2 by 2 multiplied by I hat minus a 2 by 2 j hat plus a 2 by 2 times k hat. And then you got to figure out the numbers that go in those 2 by 2 blanks. Okay, so you block out the row and column that I hat lives in, and you'll get -2, 1, 1, -2. And to be honest, I've taught this class, like I said, for 20 years, since the year 2000. A common student error, and I'm guilty of this also, because I'm in a hurry, I'll copy down these 2 by 2 guys kind of fast, and I'll probably accidentally forget to copy a minus sign, and then the whole thing goes down the toilet. And then I go, oh man, and that's going to be you, trust me. Okay, it happens. So to get the 2 by 2 j hat, block out the row and column that j hat lives in and look at the numbers that are still standing. And to get the k hat 2 by 2, block out his row and column. And now you're going to go, okay, -2 times -2, that's +4, minus 1 times 1, that's 1, times I hat, minus the major diagonal, 1 times -2, minus the minor diagonal product, 3 times 1 is just 3, times j hat, plus 1 times 1 is 1, minus 3 times -2 is -6. Be careful, because that's 1 minus a -6 there. There's a lot of negatives floating around here, and if you blow it, believe me, you're going to get just as pissed off as I do when I blow it. And so then if you write this using IJK format for the vector, there's your answer. Of course, I prefer component form, but both answers are correct, and we're done with part A. Okay? You follow the formula, it's all good. Now, what about letter B? I'm going to do letter B the slow way, even though it's kind of boring, but you're going to see what's going to happen here. So if you're doing the opposite, V cross U, yes, order matters. This isn't like the dot product. Dot product, I don't really care what order. U dot V is V dot U. You're going to see cross product ain't commutative. Pay attention. So here you're going to put the V vector first because they said so. And then you're going to put the U vector on the bottom. And then if you use the 2 by 2 determinant times I hat minus 2 by 2 j hat plus 2 by 2 k hat. I'm going to go very fast now. Okay? And then you're going to get, this is 1 minus 4, I hat minus 3 minus a minus 2, j hat plus negative 6 minus 1, k hat. And this is going to end up being, folks, check it out, negative 3 I hat minus 5 j hat minus 7 k hat, which in component form, negative 3, negative 5, negative 7. How does that compare with part A's answer? I'll open it up.
The opposite direction.
Thank you. That's exactly right. And that's important to know. So the U cross V is basically the opposite of V cross U. So that's the point I wanted to make by letter B. Now, what about letter C? So let's go to the next page. I'm going to append a page because I'm running out of room. What happens when you cross a vector with himself? Like, can you even do that? Certainly. You can, and something weird happens. Now, if you've taken a vector linear algebra class, essentially, you already know the answer, because when you're taking a determinant of a matrix and one row or column is a multiple of the other, or they're a match, something interesting happens to the determinant. I don't want to give it away, so I'm not gonna. But I've taught linear many times. That's a good class. Okay, so you're like, okay, well, if I use the 2 by 2 determinant I hat minus 2 by 2 j hat plus 2 by 2 k hat, I'm going to go 1, negative 2, 1, negative 2, 3, negative 2, 3, negative 2, 3, 1, 3, 1. Okay, major diagonal minus the minor diagonal. Major diagonal minus minor diagonal. Major diagonal minus minor diagonal. What happens? What's that?
Zero vector.
Zero vector, thank you. And a zero vector has a magnitude of 0, and essentially it doesn't really have a direction because it's pointing in all directions. So, well, what about the right-hand rule? Well, the right-hand rule is going to fail you when you try to take a cross product of a vector with itself, because you're going to get the zero vector, okay? So there you have it. I just did 3 examples of cross product, and hopefully you learned a few things along the way. Okay, now here's a very key question. This is very key, people. Can you take the cross product of 2 vectors in the plane? Remember, plane means 2D? The answer is not only no, it's hell no. There's no such thing. Really? Really. Cross product, by its very nature, can only be performed in 3D. You can't do it in 2 dimensions, 4 dimensions, 5 dimensions, any other dimensional space. It's a 3D property only. So the moral of the story is, you can write this down, cross product can only occur in 3D. It's meaningless everywhere else. Now, if you have 2 vectors in the plane and you want to pick them up and embed them in a 3D coordinate system so that their z component is 0 and make them 3D vectors and then take their cross product, that's legit. But you're changing those vectors into 3D vectors before you're taking their cross product. That's important. Okay, let's do some algebra properties of cross product. Okay, U cross V is equal to the opposite of V cross U. We just saw that with an example. So we do not have commutativity when we're doing cross products. Remember that? That's super key. If you're taking a cross product with the sum of 2 other guys, you can either do it like that, that's legit, like take the sum first and then do the cross product. But it is equivalent, and you're allowed to, quote, distribute, if you think of it as distributing, the cross product over the sum. Both sides of that equation are equivalent. Whichever is your favorite, do it. I personally think the left-hand side is easier than the right-hand side. Why? There's 2 cross products I have to perform on the right-hand side. And I hope that you get that the cross product is a pain in the butt. And it's very, very vulnerable to little silly mistakes. So if you open yourself up to making more silly mistakes by doing more than one cross product, you could very easily open yourself up to getting a wrong answer, and then you're going to get all frustrated. Okay, number 3, if you take a scalar multiple of a cross product, that's totally legit, but it's also equivalent to scalar multiple with one guy and then do the cross product, or the first guy cross product with the second guy scalars multiples. Okay, if you take a cross product of any vector with the 0 vector, this is the one and only time where cross product is commutative. Well, how come? Because you're just going to get the 0 vector every time. And we already saw number 5 on the previous page. What do you get when you cross product a vector with himself again?
Zero.
Zero vector.
0 vector. Make sure you put a little thingy dingy over the 0. If you just put the number 0, I'm going to mark you wrong, because this is the number 0, not the 0 vector. And yes, it's different. And yes, notation matters in my class. When I read your uploaded work this afternoon, every time you forget to use, like, put these little arrows on your vectors, -1 point. I'm going to train you. It's not going to be pretty. Number 6. This one I'm going to put a double star by, because this has a special name. Not Briggs doesn't tell you. It's the triple scalar product. But it says that U dotted with V cross W. And this is a dot product right here. So we're mixing now dot product with cross product. Can you do that? Sure, just so long as you keep it all straight. Cross product result is a vector. Dot product result is a scalar. So you're going to take the dot product of these two guys. It's the same as taking U cross V first, and that's a V right there, and dot producting him with W. Same thing. Okay, we're going to do another theorem. Yeah, I know this is a lot of theorems. I got to lay down the laws before we can have fun and play with vectors. What about it? What about the geometric properties? Well, some kind of fun stuff. If you've got two non-zero vectors in space and you know the angle between them, some cool stuff you can talk about geometrically, which helps you visualize better. And you already know one of the visualizations is that U cross V is going to give you a vector that's orthogonal to the two original vectors by using the right-hand rule. So that's one thing, but here's some more. So I'm just going to write down what I just said. That's property 1, is orthogonal, essentially perpendicular, to both U and V. And that's super important because the physics folks use this fact all the time. Number 2, this one's kind of cool. If you take the magnitude of your cross product, it's the same as the product of the magnitudes times sine theta. Cool. That one's a nice one. I'd memorize that one because you're going to have it on quizzes and exams. Like, I'm not trying to kid you or anything. This one is way cool. I'm going to put like 3 stars by it because I love this one. U cross V. If those two guys have a cross product that's equal to the 0 vector, what will that mean? IFF means if and only if. So you can read this sentence in both directions. It's what we call a double header sentence. If and only if U and V are scalar multiples of each other. And what does it mean from last week's material when two vectors are scalar multiples of each other? I'll open it up.
They're parallel.
Very good. Thank you. What I like about number 3 is if you have two 3D vectors, you can only do this with 3D vectors. If you want to quickly find out if they're parallel, instead of doing that whole scalar multiple business, if you take their cross product and you get the 0 vector, automatically those guys are parallel. And I hope you can see why this is true. Like if you have U here and V is parallel, so it's pointing in the same direction. If you try, putting your fingers, these are my fingers here, and then my thumb. If I try putting my fingers through that, there aren't two vectors to put my fingertips through. So I just have the one, they're both pointing in the same direction. So essentially it sort of gets zeroed out there. And finally, and I'll put a star by this because it's important, the magnitude of U cross V actually gives you some cool number. It's the area of the parallelogram having U and V as adjacent sides. I don't know if I spelled parallelogram right. I think I did. And yes, this is going to be on the quiz and in the homework this week. Yes, yes, and yes. Like if you have to ask, it's a yes. Okay, I'm going to prove number 4. Here's U, here's V. If you can imagine that these two guys are adjacent side lengths of a parallelogram, then the other two sides are going to be the dotted lines I have here. So we want to find the area of that parallelogram. I don't know if you guys remember, but area of a parallelogram for you geometric buffs, like here's a parallelogram, not a very nice one, is if you drop the perpendicular down here, this is H, and this is B here, and so the area is equal to, have you ever guys see this before? You know, it's base times height, B times H.
It's a rectangle.
But that's, well, that's, this isn't a rectangle though, George. This is a parallelogram. So the height is this perpendicular right here. There's another formula for area of a parallelogram that involves triangles. You have two bases and you add them together, take half of that and multiply by the height. This is an alternative way. So my parallelogram here, I have the base. So my area is going to be the area of the base, but that's the magnitude of U. So if I drop a perpendicular down right here, this H right here is my height, but how do I get it? So if you look there, if I blow this triangle up a little bit, so here's the V vector, and here's this H that I wish I had. If I know the angle between them, I can use a trig fact that sine theta is opposite over hypotenuse, where opposite is the H that we want, H over hypotenuse. But the hypotenuse is the length of V. So what I'm saying is if I solve this formula for H, my H is essentially equal to sine theta times the magnitude of V. So my area is the area of the base times the area of the height, which is sine theta times magnitude of V. And if I rewrite this area formula a little bit nicer, it looks like that. Now use property 2 backwards. What do you mean? If you look at property 2 in this theorem, and you look at the right-hand side, and it also means the same as the left-hand side, that's what I'm saying. So I get that these are equal, and this is the quick and dirty way to find the area of a parallelogram. And I'm done with this proof of why it's true that the area of a parallelogram is the same as the magnitude of the cross product. Cool. Okay, I got time. I'm going to use it. I don't have much time left. I know it's 9:49. I'm going to go for 10 more minutes because I can. Next time what we'll do is we'll finish up the cross product. That'll probably take some time. And then we're going to start doing lines and planes in space. I'd like to get as much of that done as I can by Friday because sometimes that's really tricky for students. Dot product and cross product, not really that tricky because it's kind of formulaic. You know, you just do the formulas and you're fine. Okay, so let's take a look at letter A here. Here they give us two space vectors. How do you do letter A? How do you find a vector that's orthogonal to both of those vectors?
If the dot product equals zero, right? Oh shoot, I've already. I don't think it's.
Well, if we were being asked to figure out if they're parallel, and it turned out we did the cross product, and the cross product was the zero vector, that would mean these vectors are parallel. But I don't think they're talking about parallel here. They want us to find a vector that's orthogonal to these two given vectors. Any ideas?
Is this going to involve projections?
Nope.
Their cross product.
Yes! Thank you! Who just said that?
Is Isaiah?
Isaiah, God bless you.
I took linear.
You've been actually awake this whole time. I think you have a pulse. Fantastic. Folks, if you've been half awake for the last half an hour, for God's sakes, people. I know, it's hard. I know we're learning remote. It sucks. I hate teaching remote, folks. Seriously, I'm keeping the suicide hotline ready to go because it sucks. Folks, once again, what does cross product give you by default? If you have two vectors and you get their cross product, you're going to get this vector here is orthogonal. In other words, it makes 90-degree angles. See these little squares down here? Those are little 90-degree angle little icons. This guy is by default. You get this for free, okay, people? Orthogonal to the two original dudes. Have I made myself clear?
Yeah, it's clear
I'll
now.
check the chat. You slept 2 hours, Nicholas Gonzalez? That sucks. Is that because of quiz 1 or what? Good God, man. Vanessa overslept. Okay. I don't know what to tell you guys. You got to have some time management when you're a college student, don't you? How else are you going to get through this pandemic?
I think the better skill to learn is time generation.
Yeah, I have a better idea. Let's go back to the future and relive this entire year. Let's start over because this year sucked. How about that?
As I go further back, like at the point you're already existing powers beyond the powers of nature and physics, you may as well to go all the way.
You know, my birthday was in March. It was a week after the campus shut down. I still have not gotten a proper birthday celebration, okay? And we're getting close to 6 months later. I feel gypped. I am outraged. I want a refund for 2020. Okay, make it happen. All right, here we go.
2019 part 2.
2019. Okay, so this is what you get for free is this is going to be the vector u cross v, people. That's the answer for letter E, A. So let's go get u cross v. Okay, let's do the 3x3 determinant method. Top row has I hat, j hat, k hat. Second row has the u vector components. What are they? -3 what? 0, thank you. 1. And then put the v components on the bottom row, 2, 2, 2. So this will be a 2x2 I hat minus 2x2 j hat plus 2x2 k hat. Block out the row and column that I hat lives in. Block out the row and column that j hat lives in. Block out the row and column that k hat lives in. 0 times 2 is 0 minus 2 I hat minus. -3 times 2 is -6 minus 2 times j hat plus -3 times 2 minus 0 k hat. So this is going to be -2 I hat minus -8 j hat plus -6 k hat. And a negative is a positive. And I'm going to write this in component form because that's just my personal favorite. And there you have it. There is a vector that's orthogonal to the two original dudes. And now let's do parts B and C and we'll wrap it up for today. Letter B, find the area of the parallelogram that has the U and V as two adjacent side lengths. Okay, any idea how to do this part B? Somebody help me out.
Find the magnitude of u cross v.
Rosie, God bless you. You're still alive. You're awesome. You get what's behind door number 3, the Bendix washer dryer. Does everybody see that Rosie has it? That all you need to do to get that area of that parallelogram is take the magnitude of the cross product of the two vectors. Well, good news, we already have the actual vector in hand because we did that part in part A. And then you just have to find the square root of the sum of the squares of these puppies. What the heck is 4 plus 64 plus 36? 104. And it turns out, believe it or not, folks, that 104 is 4 times 26. And the reason why that's important is I'll dock you a point unless you completely simplify your radicals. So there is the area, and I don't know what the units are, but it's some units squared. Who knows? They didn't give us. And then the letter C, here's the weird part. I didn't give you how to find the area of a triangle, having U and V as adjacent sides, but I'll draw a picture. Here's a triangle having U and V as adjacent sides. How do you find the area of the triangle that has the U and V as adjacent sides? Well, here's the fact you're going to use the to help you get the answer. Do you notice that a parallelogram is simply equal to two triangles stuck together? Say yes.
Yeah.
Thank you. And they're two equivalent triangles, like there's one triangle and then the green one is the other. Here's the parallelogram right here. So you know how to find the area of a parallelogram. We just found it. It's just simply the magnitude of the cross product. So what's the obvious way you're going to get the area of the triangle? Quick. Thank you. The area will equal half of the magnitude of the cross product. So you're going to go, oh, this is going to be a half times 2 times square root of 26, and then the 2's cancel, and your final answer is square root of 26, some units squared. And I'm officially done with today's lecture. Congratulations. We'll complete the cross product guide next time. As far as quiz 1, you can't review it yet in my math lab because I'm not going to open it up yet. I want to grade it first. And then when I give your stuff back on Wednesday, I'll open up my math lab and you can review each problem and see what you answered and if it was right or not or what have you. Even if you answer it right, you might have some points taken off if your uploaded work did not match. Okay? Further, I do want to say that I don't give out solution keys for your quizzes and so on this semester. I mean, when we're face-to-face, I like to give out solution keys, but now it's my math lab. You'll just use my math lab to help you review. And the homework problems are basically the problems I put on there, so go back in your homework and use view an example button. However, if you want to come to class a little early Wednesday and do some solutions, I'll be happy to meet you before class. We could go over whatever problem you want to look at. Or come to my office hours Wednesday or Friday and ask for looking at a solution. I'll be happy to do for you, okay? So that's another way you can get the solution keys, okay? Other than that, I'll stay for a couple more minutes in case anybody has last minute questions, okay? See, Nicholas' 21st birthday sucked. It was a week ago. I'm so sorry. Happy belated birthday, though. Any ideas? Karaoke bar, gaming tournament. Oh my God. That sounds like what hell would be like. Sorry. Well, my girlfriend's really good at singing, so she would love it. Okay. Besides trying to figure out some good birthday celebration ideas, does anybody have any Calculus 3 questions?
I have a question, Professor.
Sure.
I was a little concerned about the formatting in my lab. If it turns out in the really rare case that like you did get the answer correct,